So the next class of vulnerabilities we're going to cover is the denial-of-service vulnerabilities. This is known as contract bricking, and it can include a lot of different things: gas limit reached, unexpected throw or kill, and then contract takeover. An example of this is to trick payments to a malicious contract with a fallback function that's basically an infinite loop. And if you require that that thing actually finish in order for your contract to function properly, then you've just bricked the caller, the calling function. So here's a scenario. An auction contract allows a user to bid on different assets. And then the user calls this bid function, and it's a payable function where it sends the amount of ether that it wants to bid on the object for. And this is basically using the auction contract as an escrow, right? So this is sort of like forcing you to commit the money so that when you are the winning bid, it has your money. It doesn't have to ask you for it later. And so the contract is always going to hold the full value of the highest bidder's bid. And this is until the auction ends. The contract contains a withdraw function that allow the contract admins to retrieve funds from the contract. And then this function sends the amount to a hard-coded admin address. So nobody can hijack it and get it sent to themselves. So the recipient of the withdrawal is always the admin. But the developers have accidentally left the function public. And so what an attacker can do to launch a denial-of-service attack is to continuously call withdraw and direct all of the contract's ether to the admins. And so what this ends up doing is it blocks any of these auctions from completing, because when you want to complete an auction, you have to take the escrow funds and send it to the object's owner. But if you've wiped out the contract, wiped it out in that you've sent all the ether to the contract admin, then there's no money there to actually pay out the bid. So you could so the admins could basically return the escrow ether back to the contract by calling the fallback and then returning the ether, but the attacker can just continuously do this. So that is a denial-of-service attack on the contract. So it's just an example. So some real examples of this. Governmental was a smart contract that had a denial-of-service due to lack of gas. So it's a different kind of vulnerability. And so in governmental's in its jackpot payout, one of the things that it did was, so you have a bunch of participants who are putting money into this smart contract, and then on paying out, periodically this contract would pay out money. This thing, when it does the payout, what it does is it resets all of the data structures within the contract so it can then run again. The problem is that if this is in your payout, and if there are a whole bunch of addresses in this payout, one of the things that this will do, clearing out the addresses and the integers associated with it, is that it will iterate over every single entry, going to the storage locations and then deleting it one by one. This is a computationally expensive operation. It looks like 2 lines, but when you look at the gas consumption, if this thing is unbounded, or if it's really large, then this will end up consuming a lot of gas. And so for this particular contract, it got large enough, there were enough participants that the cost for these 2 operations ended up being this 5 million in gas, and then the block limit was 4 million. So immediately you're not able to do the payout of this contract because you have a data structure issue in your algorithm. Yeah.
What sets the gas limit? I know it's like consensus among the miners, but like
who determines that? That's a good question.
Has it been changed in the lifetime of
I don't know, actually. Yeah, but it's set by the network based on its estimate of what the full node can handle. Yeah.
Because if I was the lucky winner of $100,000 worth of Ethereum, I'd lobby for the gas limits.
Yeah, and if somebody didn't want you to win that, then they would keep on playing, assuming that you could still like put stuff into there to keep it always beyond the block gas limit. Yeah. Yeah, so so that's definitely another vector of denial of service to keep it going, yes.
Is this on the next slide, but did they resolve this? Or is this kind of stuck?
I think it's kind of stuck, but
So if the contract owner built in a way for them to extract all of it to themselves, could they then pay the...
Yes. Yeah, they
Well, they're also held accountable for doing that. You can track an Ether scan to see which address it went to, but...
This is why a lot of smart contracts now will put in a backdoor for the admin to go in there and wipe out the contract and then potentially do something else. An emergency kill switch, which is good for the contract owner, maybe bad for the people who are buying into the smart contract. Yeah. Okay, here's another one. This is a parity bug that we've actually covered before. Because this is an access control vulnerability that ends up leading to denial of service. And so this was the init wallet one where anybody, it was missing, first of all, it was missing the internal call. So when you included that library, anything that was public could be called via the delegate call. I don't know if you remember that from last class. That delegate call would not have worked if the internal keyword was used on a init wallet, so that it could only be called from within. And so this ended up causing anybody who built a wallet using this library ended up having their funds bricked on this one. Here's another one, and it was parity again. In this one, an adversary compromising this library by basically self-destructing it. So there was a component that all of these parity multi-signature wallets were depending upon. So there was this library code, and as it turns out, the library had a notion of an owner, and this vulnerability allowed the person to set the owner of the library contract, similar to the previous one. And then self-destructed the component in the library. And anyone who had included this library, basically their wallets were bricked. So similar exploit, but these are two different issues with the parity smart contract. Okay, so here are some simple examples in code. Here's a contract where you pay to become president, and the price doubles on every transfer. So here's the function to try and become president. It's payable. You need your message value to be greater than the current price to become president. And if so, then you pay the previous president. So the president variable stores the address of the current president. So you pay that president a certain amount, the amount of money that was sent. And then you crown the new president to be the message sender, whoever sent that value, and you double the price to become president. So this actually looks reasonable, except the previous president could be a smart contract. So if it is a smart contract, when you do this transfer, this is going to call the fallback function of the previous president. Okay? Typically, the transfer call will execute it will send 2300 in gas to the original president to execute the fallback function. So 2300 in gas is the magic number for the gas that you need to receive payment on the blockchain. So if you're a wallet, you need to or a trivial smart contract that has a trivial fallback function, you need 2300 in gas to receive that money on your fallback. If your fallback function is actually a loop, an infinite loop, for example, then this is always going to fail. right? Because the transfer call is only going to forward 2,300 in gas, okay? And then this failure of the call allows the previous malicious president to remain forever, or to basically cause this thing to always fail, is the idea. Okay, here's another example. The vulnerable function iterates through all the player IDs to select a winner to reward. This is similar to the governmental one. If you are able to inject a player ID that's really large, so that this is larger than the amount, this is large enough so that the amount of gas that you require to do this loop is beyond the gas limit, then you will also brick this particular contract. Okay, so with that, I'm going to do a walkthrough of Lab 3.6. So 3.6 is the record label level. So the record label contract, the first thing is, the first thing that the record label contract does is that it creates two things. It creates a manager contract and a royalties contract. So you are an artist, so the player is the artist. The artist has a manager, and the manager takes a huge amount of the artist's profits for this record label. And then there's also a bunch of royalty receivers. So you can specify if, for example, you have band members, you're going to take the money that you get from funds for the record, you're going to distribute a certain cut to the manager, and you're going to distribute a certain amount of those royalties to each of these individual receivers. Okay? It has a payable constructor that will take the initial ether that you instantiate the level with, and it'll identify the manager contract, and it will set the manager contract actually to the CTF launcher, and then it will create a royalties contract. Now this contract is responsible for divvying up the funds and distributing the royalties to all of the receivers. And then it's got an external, it's got a payable fallback function to add to the balance of the contract. Okay. So the simplest part is the manager contract. It's just instantiated with an owner, and then when the owner calls withdraw, it'll transfer the balance back to the owner. This will never get called though, because we're going to try and bypass. We're trying to cut the manager out in this contract. Okay. So the record label contract, the first thing to look at is this withdraw funds and pay royalties. This is sort of the heart of the contract. This allows authorized accounts, and this is basically the artist, to initiate a payout. So the contract has been getting a lot of money from record sales, and if the artist wants to all of a sudden collect some royalties, it will call withdraw funds and pay the royalties. And it will say how much of the revenue do I want to be distributed. And that's what the withdrawal amount is. And hopefully the amount that you're trying to distribute is less than or equal to the total number of funds on the contract. And then what it does is that it subtracts that. If it is, in fact, there, it subtracts the amount from their funds. And then it calls the royalty contract. So the royalties contract is going to then distribute the funds to all the players. And so it calls the royalties fallback function. And the fallback function in the royalties contract will then distribute the money. Okay. The royalties contract, after it has distributed the funds to all the different people, the royalties contract will then send the remaining ether back to the record label contract using this collect remaining funds. So we'll see when we go into the royalties contract, this thing will eventually get called by the royalties to send the money back, what's remaining back. And you can see it requires that the only person who can call this is the royalties contract. Okay, so then after the call has been, the royalties have been divvied up, the royalties contract is going to pay back the remaining funds. And what this record label contract wants to do is it wants to figure out how much is left in the withdrawal amount. So the way it figures out how much is left over from this withdrawal amount is that within the royalties contract, there is this get last payout and then reset. This will get you the remaining funds that were left over, or that were distributed. And then you can calculate the amount that you can pay yourself by subtracting out the royalties paid. So you figured out how much was distributed to the manager and all of the other receivers of your royalties, and then you can pay yourself back out the difference between what you withdrew, what you wanted to withdraw minus the distribution of royalties. And then you send that back to yourself. So that's how the contract works. This is the royalties contract. It's got the collections contract, which is basically the record label. So the record label is the collections contract that will then call the royalties contract to distribute payment. It's got the address of the artist, whoever the money is going to go to. It's got a mapping of the royalty receivers. So these are the folks who are going to who you're divvying up the payment to. And as part of this, it's got a mapping that goes from the receiver addresses to their cut of the profit. And that's what, because you need to distribute the royalties based on some kind of percentage. The other variable is the amount remaining. And it turns out this is not going to be used, but we'll get to that later. And then this variable, the amount paid out, this is, so as you go through each one of the receivers, you're going to distribute all the ether to these receivers, and then you're going to keep track of that variable in amount paid, so that when you get called by the record label contract to say, how much have you paid out, it will return this one. Okay. So the constructor sets the collections contract to only the record label contract, sets the artist, and the first thing it does is it initializes the manager. So we instantiated this with the manager. Only the manager contract is added to the royalty receivers. So you add it to the mapping of receivers, and then you set the profit for the manager to 80%. And the percent remaining is 100 minus that, so it'll be 20. There are two modifiers that are implemented. One is to make sure that only the record label contract can call certain functions, and the other one is only an artist, only the original artist can call another call another set of functions. It also has this payable fallback function. So this is what the record label calls, and when you are called, you want to make sure you're only accepting payment from the collections contract or the record label contract, and then you call the payout royalties call. And so for payout royalties, it goes through this array of receivers. So this is the call to it, and again, only the collections contract can do this. So you iterate through all of the receivers. You set the current address to whatever part of the array you're at, and you calculate this receiver's payout. So this payout is the amount in the sort of the funds that you're trying to distribute. You multiply that amount by the percent of profit. So in this case, if this was the manager, this would be 80, and then you divide it by 100. And then this payout will be that cut of the original ether, and then you send that receiver that amount. And then you add the amount that you paid out to that variable. You update the amount that you paid out. Okay, and then finally, After you're done with this loop, you can call back into the record label contract to whatever is remaining that hasn't been paid out, message.value minus amount paid, you can send that back to the record label contract so that the artist can then pull the money back from the contract. Okay, another function that's implemented is add royalty receiver, and this allows the artist to add different people that the artist wants to distribute the royalties to. So you can see here it's protected by isArtist. The percent that you allocate has to be less than what's remaining, so it has to be less than 20 initially. And then what you do is you push the receiver and you update its percentage to whatever you have specified as the percent, and then you subtract from the percent remaining the amount that you've allocated to that receiver. Okay. The last thing that's implemented is this allowing the record label contract to determine how much was paid out. And so this is the get last payout amount and then reset. So the record label contract has to figure out how much the royalties contract paid out so that it can then allow the artist to withdraw the remaining. So if you remember this call, this is where it figures out the get last payout so that it can subtract from it and then pay out the artist. So that's the final piece of this contract. Okay, so that is a lot to get your, I mean, it's not a lot of code, but it's the complexity, it grows very fast. Are there any ideas in terms of how to attack this, this smart contract? How would you figure out a way of writing out the manager from what you have seen? What are some strategies? You as the artist, say you're acting as the artist and you want to figure out ways of interacting with these contracts to zero out the manager. Any ideas? Was it? This is 3.6, yeah, record label. It's actually up there on the slide right now, what you could do. You can add the manager and put 0%. So if you look at this code, if you remember at the initialization, we added the manager and then we set the profit of that manager to 80. This call takes any receiver, adds that receiver to the mapping, and then sets the percent of profit to whatever we specify. So this is the vulnerability. The royalties contract is not expecting you to add the manager again. And this allows you to take that 80. So when this, if you call this with the manager address and 0, then you're going to basically overwrite what the constructor had initialized to 80 in the previous screen. So that's the vulnerability that leads to denial of service. So the level walkthrough, this is the contract address. You're going to need to figure out, as part of this, your addresses of the manager, and not the manager contract, and then the address of the manager itself. You have to figure out both of those. You have to figure out the royalties contract address. So there's a little bit involved in actually doing the exploit, and this is what the walkthrough is going to go through. You get the CTF level contract first, and you figure out the addresses. You have to figure out the addresses of the royalties contract and the manager contract. So in the constructor for record label, it creates both. And so if you go to the record label contract, which is, in my case is this 8DD address, you can see that as part of this contract creation, it created two other contracts. And the earliest one is the manager contract, and then the next one is the royalties contract, because the royalties contract requires a manager object in order to be instantiated. So this is why the manager contract is created first. And then from the manager contract, you have to get its address. Now you need to figure out, so the manager contract gets instantiated with an address, and the address is the owner. It's the manager itself. And so what you need to do to find what the owner is you need to interact with the manager contract in MyCrypto. And one of the ways to do this is to copy the manager code into Remix, compile it, and then get its ABI. Because MyCrypto needs the ABI to interact with this contract. So that's what you would do. And then you go to the manager contract address, and then access the owner, and you'll see that the owner is this address. This is the address that you want to add as a royalty receiver to zero out the royalties, because this is initially the royalty payout on this person is initially 80. Okay. Repeat to get the royalties contract, to get the address of it at least, and then you're ready to go. You can go to the royalties contract and then add the manager as a royalty receiver. So because you're the artist, it's the CTF player is the artist. You can then call into the royalties contract, you add a royalty receiver, you paste in the manager address you got previously, you set the % to 0. And then all you need to do is withdraw the funds from the royalties, from the record label contract, and then you'll get, you withdraw the entire balance of whatever is there, and then you'll win the level. Okay. So hopefully you should be able to do the record label level pretty quickly. So the next set of vulnerabilities is the unchecked return values for low-level calls. There's no level associated with this one in the CTF, so I figure I'd just cover it now and then let you finish the levels that I just walked through. So what is this vulnerability? This is also known as silent failing sends and unchecked sends. And what we have seen so far in Solidity is that if you have an error in any of your functions, you'll throw an exception, and that the state of the blockchain will be reverted. Now this happens for pretty much every call except for these low-level calls. And so these calls, call code, delegate call, which you've actually seen before, and send, if you call these things and they go into another contract and they fail, the return value, the exception from that failure won't cause an exception in the caller. Those things, these particular API calls, they will just return true or false as to whether or not they've succeeded or failed. If you really want to roll back the entire transaction, if one of these calls fails, you have to manually check the return code and then do the revert yourself. You do the exception yourself to roll back all of it. Okay? So they're not propagating. And everything up until this point, the exceptions do propagate. So in Solidity, these calls should be avoided whenever possible, unless you know what you're doing, is the caveat to that. Okay. So here's an example, a walkthrough scenario. You have a game where players pay to become king. This is similar to the president contract from before. You pay the claim price to get the throne. The contract sends some commission to the previous, sends some commission to the owner of the contract, and then sends the result to the previous king, and then makes you the new king, and then doubles the throne price. So the usurper pays this new price to depose you. The contract sends you the payment, less than a 1% commission, and it makes the usurper the new king. But when sending the payment to you, if you're a smart contract, if the king contract sends you the default 2300 ether, and you have some code in your fallback function as a smart contract, then you'll never get this, right? And and the throne gets transferred, but then the deposed king or queen never receives the payment. So unchecked calls, this is not a problem because you made your own bed as a smart contract, but you can actually use this vulnerability to launch a denial of service attack. So here's a real example, King of the Ether Throne. It's a similar idea, and it had this vulnerability where this unchecked send bug allowed the contract to completely lock up. Okay, so an example of a denial of service attack is shown here. This is a fundraising contract, so very similar to the fundraiser that you ran earlier. You get a bunch of money, and then if you don't meet your goal, then you go back and you refund everybody's contribution. So this is what this contract does, and this is done in, this is not Viper, this is the precursor, this is Serpent, which is a Python-like smart programming contract, so it doesn't look like Solidity. But basically what this function is doing is that for all of the donors, it's trying to send the donor the amount that that donor had contributed back in a loop, okay? And so the send call, the semantic of the send call is to forward all of the gas for the, to the fallback function of the donor. And so as you're paying each one of these donors, you're paying it through the fallback function. And you're forwarding all of the gas that was sent to this campaign ended function to this donor fallback function. If the donor's fallback function is an infinite loop, then this prevents any donor beyond that infinite loop from getting any money back. And this locks up the donor's funds in this campaign. Okay? Do you see that particular vulnerability? Okay. So the remediation is to always use this address.transfer call, which is what we've mostly been using. Address.transfer throws an exception on failure, and it causes the whole thing to abort. The caller transaction to abort, not just the transfer one. And it only forwards 2300 in gas. And this makes it safe against reentrancy, which we'll talk about in next week. Avoid the low-level calls address.send. So this will return false on failure instead of throwing an exception on failure. But it also only forwards 2300 in gas, so it makes it safe against reentrancy. And also avoid this low-level call, address.call.value.gas, and this will force you to send all of your gas to the fallback function. So this also returns false on failure, but then it does, because you have called it this way, it does forward all the gas to the function that you're calling. Now, there are cases where you do want the low-level calls. If you know the amount of gas that you need to consume on that call, but basically, these things should be avoided unless you know what you're doing. Okay, another thing to do is to check for call failure if you're using this low-level call. So here's an example where the game is ended and you're trying to pay out a prize. And naively, you can send winner.send the amount of ether. But then this thing can get locked up if the fallback function consumes too much gas. And so what you would want to do is you would want to say, if this returns true, then you say you have paid the prize out. Otherwise, you throw an exception. So this will allow you to bubble up the exception. So if this fails, then you can revert the entire thing. The other thing is if you have something that's similar to this where you need to pay out money, rather than the contract paying the money, you can have the recipient withdraw the money. And then when the recipient calls your withdraw function, the recipient's going to actually send the gas needed to get the money back. And then hopefully that puts the onus on the recipient, not on the contract. Okay, so that's all I wanted to cover for today. I'll let you just do the labs for the rest of the time. Are there any questions about what we've covered today? Okay, I'll let you get to work.